Hello! In this video we will learn about the parallel axis theorem, which is a handy way to compute the moment of inertia. Imagine we had these three objects attached together, and we will consider the objects to be point masses. All objects have the same mass. I have marked the center of mass with that red dot and the letters COM. If the system was free to spin about this axis, what is the rotational inertia of this object? Well, as we learned previously, we simply need to find the rotational inertia of each point mass and add them together. So both of these objects have a rotational inertia of m times d squared, since little d is their distance to the axis. This object is on the axis, so it doesn't have any rotational inertia. So our total is 2md squared. Now what if the axis did not pass through the center of mass, but instead passes through over here, a distance of big D away? Well, we can recalculate the moment of inertia with respect to this axis. This mass contributes in m times big D squared. This mass contributes in m times little d plus big D squared. Just pause for a second if you can't see why the total distance for this object is big D plus little d. And this mass contributes m times big D minus little d squared. Again, big D minus little d is the total distance for this object. This is kind of a messy equation, and we had to figure out what the distance of each object was, which can get tedious. There is a better way to do this. There is something called the parallel axis theorem, which states the following. The moment of inertia of an object through any axis is equal to the moment of inertia of that same object through its center of mass, plus a term. This term is the total mass of the object times the distance of the object's center of mass to that axis squared. To show what this means and how it is useful, let's apply it to our example. In our example, we want to know what the rotational inertia through this axis is. We happen to already know what the rotational inertia is when the axis passes through the center of mass. It is this formula, which we already worked out. We also can see that the distance between the center of mass and the new axis is given by big D, so that will be the big R in our parallel axis equation. Finally, we need the total mass of the object. Well, there are three objects of mass m, so the total mass is 3 times m. So parallel axis theorem tells us that this is the moment of inertia. If you were to work out the algebra of this expression from before, it would simplify to the same expression. But the parallel axis theorem was an easier way to do it. The only trick might have been finding the center of mass of the object, but in this case it's obvious where it is in the x direction, since all masses are equal and the two objects are equidistant from the central object. The parallel axis theorem is even more useful in the case of continuous objects, like a circular disk, a sphere, or a rod, whose masses are evenly distributed throughout. For objects like this, we can look up in a table what their rotational inertia is, but that value will usually be when the axis passes through its center, which is also its center of mass. Using parallel axis theorem, we can find out what the rotational inertia will be when the axis passes through anywhere else. Let's do an example with a thin rod. M is the total mass of the rod, and L is its total length. This formula that we are given is for when it rotates about its center. But let's say instead you wanted to swing it by its end, like a windshield wiper, or kind of like a baseball bat. What is its moment of inertia in that case? We will use the parallel axis theorem. We know what ICM is, since that can be easily looked up. The only question is, what is big R, the distance between the axis and the center of mass? Well, the rod has a length of L, so the distance between one end and the center is L divided by 2. So let's plug that in. After squaring everything, we get this. We can see that both terms have a common ml squared, but to add them together, we need to make a common denominator. 12 is the easy choice, so we multiply this term by 3, both on top and bottom. Then we add them together, and we get 4 over 12 ml squared, which reduces to 1/3 ml squared. Great! That's our answer. Finally, one more example, just to demonstrate an important point. Imagine we take a quarter, which has a radius of about 0.01 meters, and put it on a string of 1 meter length, and we swing the quarter around. What will be the rotational inertia? Well, the rotational inertia of the quarter through its center of mass is given by this formula, since it is a disk, where that little r is the radius of the quarter. Using parallel axis theorem, we can write this expression, since the axis of rotation is at the other end of the string, so the total displacement from the quarter center is the sum of r and d. Plugging the numbers in, we get this. If we do the arithmetic, we get this value. Now, let's say we thought about this for a second and said, hey, the quarter's radius is so small compared to the string's length. What if we just treated the quarter like a point mass? In that case, the rotational inertia would simply be the mass times the string length squared, which gets this value. That's about a 2% difference in the answer. Depending on the precision you need for your answer, that difference might well be insignificant. If the string were instead 2 meters, we'd be dealing with a difference of 1%. So if the object is really small compared to the distance from the axis, you're usually pretty justified in just using the simpler formula for a point mass. In fact, since nothing is actually a point mass, it is this reasoning that makes the concept of a point mass ever come into play. Sometimes we can reasonably treat a small enough object like a point mass. That's it for this video. Thanks for watching.